Okay, second one, principal component analysis. Probably all of you have already heard about principal component analysis so far, and it's actually a very, very popular approach. Even people that do not know too much about data mining, artificial intelligence and machine learning and stuff like that, but they know about principal component analysis, and they know that you have to apply principal component analysis before you do any magic. Well, that's only half of the story, of course, but anyway, principal component analysis is very, very widespread. People use it a lot, but we will see that PCA has a very, very clear and strict assumption. And if you don't know the assumption and just do it and just apply it, then you may be misled. Yeah. So we will talk about this basic assumption, of course, and this is just a kind of try to keep your focus. So like the usual podcast about this, all those conspiracy theories, they try to catch your eye with, oh, the best is yet to come, the best is yet to come, the best is yet to come. So also here, the best is yet to come. So you have to be very clear about the assumption of PCA, and we will talk about that. Yeah, but before we talk about that, we talk about what is the idea of principal component analysis and how does it go. Yeah. So we start with the motivation. We consider the grades of students in physics and statistics. Okay, so here is actually the data set. Yeah, we have, so each point is a student, and each point is measured in terms of physics grade and statistics grade. So if we want to compare among the students, so discriminate, find patterns, compare, yeah, good or bad students, which of the two grades should we take? Which of the two grades are more discriminative? Well, discriminative is of course also again politically incorrect, but in that case it's obviously physics, yeah, because the variation along this axis here, this is the physics axis, the variation along the physics axis is of course much larger than the variation along statistics. Yeah, so having a larger difference in the physics grade has much more predictive power, or much more explainability, or much more significance than a difference in the stats. Yeah, being the best in stats, comparing the best grade in stats and the worst performance in statistics is much less significant than comparing the worst stat in the worst grade in physics and the best grade in physics. There's much more difference because the variation along this axis, along this feature, is larger. Okay, keep that in mind. So suppose now the plot looks a little bit different, like this one here. So again, what is the best way to compare the students now? So if we look at the individual variations along each of the features, statistics and physics, well, the variation is more or less the same. So could we use both? Well, we could use both, or just one, and actually selecting both, one of those will be okay. But to be really, I mean, in the same sense as here, to be optimal in a kind of sense, we should take a linear combination of the two grades that actually represents exactly this direction here, the direction of highest variance. Yeah. So if we want to do the same game as here, where we took the feature with the highest variance, well, here the two original features have the same variance, but we could derive a new feature, which is a kind of linear combination of the original features that actually provides the highest variance. Yeah, and this would be the best direction to get the best results. Yeah. To get the most significant results, because the variation is highest. And that's actually the idea of PCA. PCA actually returns exactly two principal components in that case, two because it's a two-dimensional data set. So as a rule of thumb, we will have that later on, as a rule of thumb, spoiler, PCA for a n-dimensional data set always returns n components, principal components. And these principal components actually are the directions, and the first principal component gives the direction of the maximum spread, of the maximum variation of the data, like this one here. Yeah. So in that, this is the same example as before. So the red principal component is the first principal component actually that is computed by PCA, and gives you the direction with the highest variance, which we want to use to discriminate between the students. Yeah. The second gives you the direction of the maximum spread perpendicular to the first one. So in that case, you only have one chance to find a perpendicular component to this one here, because two perpendicular vectors will span the whole two-dimensional feature space. So the second one will be this one here, which is perpendicular, orthogonal to the red one here, yeah? Which is in that case the direction of the second highest variation. Since we only get two PCs, principal components, it's also the one with the lowest variation, but that's a different story. Okay, so before we talk about how to compute all that stuff, we should talk about normalization, because PCA typically only makes sense on normalized data. So a feature can be normalized by many different procedures. Say in the statistical domain, in statistics domain, it's mostly by subtracting its values with the mean, which is denoted as x prime, and dividing by the standard deviation, so which is denoted by Sx here. So the new feature, the normalized feature, will be the original feature minus the mean, the original feature value minus the mean times the standard deviation. That gives you the normalized feature value for a given point of a given feature. So here's the example why that is good. So consider the following body heights measured in different units. So here is centimeters, meters, and feet. So person A is 180, which is 180 centimeters or 1.80 meters or 5 feet 91, what is that, inches or whatever, 9 feet 91. Yeah. And the second one is 1 meter 72, so 172 centimeters, and so on and so on. And the third person, something like here. So the mean and the standard deviation is computed here. So the mean for the body height feature is this one here, and the standard deviation is this one here. The mean for the body height feature in meters is this one here, standard deviation this one here, and the same for the feature in feet. And after normalizing all those values, so now we can normalize the body height value in centimeters of person A by subtracting the mean and dividing by the corresponding standard deviation, and this value shrinks down to this one here. And the same holds true for this value actually, using this mean and this standard deviation. We'll get the same value here, of course, and the same for feet. Yeah. So after normalizing, we always get the normalized body height here in that case, no matter which unit we use. So the units, and that's the key observation, the different units get or become comparable after normalization. Yeah, and you can do, of course, the same with person B and the same with person C, which ends up in those two values here. And now for this normalized body height feature, the mean now is 0 and the standard deviation is 1, which is the typical normalization goal in statistics, where you try to normalize all features so that the mean of the feature is 0 and the standard deviation is 1. Okay, so normalizing all features in the dataset can have several advantages. Of course, we basically discussed that, but just summarizing them, it puts all features into comparable units. Yeah, so we make sure that all normalized features have a mean of 0 and standard deviation of 1. And that is very beneficial because it can avoid numerical instabilities in algorithms. So, for example, if a feature has very low or very high values, consider, for example, age and salary maybe. Yeah, so the age is typically something between 0 and maybe 100, 120 maybe. Yeah, but more or less between, I don't know, for employees probably between 16 and 60 something, 70. But the wage, the income can be something between, I don't know, 450 euros per month up to, or even 200, I don't know, up to, I don't know, 1 million per month. Is that feasible? No, whatever. Yeah, so the feature values have a much higher spread, and the actual values can be very, very different. And if you normalize those two features, age and salary, then you probably at least get them comparable, because they become comparable from the numerical point of view. If that makes sense from a semantical point of view, that's a completely different story. Yeah, but from the mathematical point of view, they get comparable. So it helps computing meaningful distances between observations, because there is no feature that dominates the other features. So if we just take age and salary and we compute a distance that takes both features, like the Euclidean distance, take both features as they are, then the salary values may dominate the age values, just because the distances between the salaries are much higher than the distances between the age values. So those parts of the distances will dominate the final distance values. Yeah, and well, finally, if we want to find directions of highest variance, which is somehow our goal, keep that in mind here. Yeah. Then it might be better if we do this on normalized data, so that both of the or all of the features that contribute to those correlations are somehow comparable. If they are not comparable, those correlations may also be a little bit ambiguous or biased or whatever, and at least they will be biased towards the features that have a higher variance per se. So normalizing before we do the PCA, before we try to find the direction of highest variance, might be a very good idea. Yeah. So that's why people typically use normalized data or normalize the data before they apply PCA. Okay. Yeah. As I told you before, there are many ways to normalize, but here for those slides here, we will use the notion which I already told you is common in statistics, where we try to normalize the features in a way such that the mean is always 0 and the standard deviation, so the variance is always 1. Yeah, and then the covariance of two normalized features, x and y, those are the two features that are normalized now, is the same as the correlation of the non-normalized features. So we can use, or we can work with the covariance, which is mathematically a little bit easier to work with than the correlation. Yeah, you can prove that. Just have a look on this one here. This is the actually the covariance between x and y, the normalized x's and y's, which is, if you just reformulate the whole thing, equals the correlation between those two original features actually. Yeah, so here are this is the correlation between the original features. Yeah, and the proof is very easy. It's just, kind of rearranging everything, recomputing, but anyway, we will not, it's just filling in the things here, as you see. Yeah, it's just filling in the definitions here.